Hello, hello. This is part two of chapter 5 over gases. In the previous video, we talked about physical characteristics of a gas as well as the kinetic molecular theory that helps explain. Well, now we're going to look at some gas laws which allow us to make predictions about the quantities. So it starts off by looking at four measurable quantities we can assess for any gas. So there's the quantity, so literally how many atoms, molecules, or grouping them together of moles are there. Next, we have the volume. So how much does the gas, how much space is it taking up? And so typically measured in liters. Then there's the pressure. So what force exerted over what area is that gas exerting, measured typically in atmospheres. And then how much kinetic energy does the gas have, measured in Kelvin? Again, that's a measurement of temperature. So what we're going to see is that all four of these are interconnected. If you change one of them, you change at least one of the others. You might hold one constant and cause a different one to change. But based on these quantities, there's several scientific gas laws that were discovered in the late 1700s, early 1800s. Again, way before we had any idea of what atoms and molecules were. Again, these gas laws don't specify why it works. It just shows us that it does work. So the first one is pretty simple. If you apply more pressure to a gas, what you'll find is here we're seeing the volume drop from 100 to 50 to 33 as more mercury is added. And so very simply, as pressure goes up, the volume of the gas goes down. So the more force you exert, we're going to see higher pressures and lower volumes. So we could this scenario is shown here where it can either lower the pressure and volume goes up, or increase the pressure and volume go down. And I do need to mention that for all these gas laws, we're typically assuming the other two are held constant. So graphically, if you plot this, you get this kind of weird slope of a curve. At any point on this line, we'll find. So we can say if you increase the pressure, so if it gets higher up here, we're seeing the volume decrease, get smaller and smaller. Or as you raise, we look at the largest volumes, it equates to the lowest pressure. So at any point on this line, if you were to take the two values and multiply them, we would find that they equal a constant. So 0.6 times 2 is 1.2, and 0.3 times 4 is 1.2. So the product of these two is a constant value. So to get our first law, known as Boyles Law, we're going to say, well, if these are the initial conditions, and then we change it to get a new P and V for a different, the product will be the same. And so P1 times V1 is equal to P2 times V2. This is our first gas law, and it shows that gases are inversely proportional. Now, we can go back and look at the kinetic molecular theory to explain it. So we're seeing that as the volume gets smaller, it's not that the particles are moving faster, but with a smaller area, they're able to collide more frequently. And anytime there's more collisions, that equates to more pressure. So going back to this equation, that pressure is force over area. Again, if you decrease the area, that is to decrease the volume, it's going to make the pressure go up. But the particles are not changing speed. We see this come into play. If you've ever gone scuba diving, you might know that there's different certifications you have to take, whether you can scuba just under the surface or whether you're going deep sea diving. So if you dive down, what you probably know is that as the deeper you go, the higher pressure there is. And Boyle's law would then say, actually, that's not the part we're most interested. It's not as really that hazardous diving deep. It's when you ascend. So when you come up, As the pressure drops from Boyles Law, we know that as pressure goes up, volume goes down. Well, think of now the opposite. As the pressure goes down, the volume goes up. And so as the pressure drops off rapidly, you can get gases that were dissolved in your blood to come out, and then they expand. This leads to what's called decompression sickness, aka the bends, and it can be deadly if you're not treated for it. Another example of this coming to effect is some deep sea fishermen who can pull up some fish that are normally found thousands of feet below the sea. This is the blobfish, which looks pretty ugly, but that's what you have to keep in mind is it doesn't normally look like this. It lives in an environment that has pressures of 800 to 100 atmospheres, but when you pull it up rapidly, all the gases start expanding and cause this thing to look like this. The next law we have is Charles's law. So this one, instead of seeing a change in volume with pressure, this is with regards to temperature. So this one's pretty straightforward. You probably know you shouldn't throw like a closed container of something into a fire because it could go boom. And that's because as gas particles move faster, there's more collisions and it's going to generate more pressure. Or in this case, if the pressure is constant, the volume goes up. So instead of being inversely related like pressure and volume, volume is directly proportional to temperature. So temperature goes up, volume goes up. Again, we can think of this with more kinetic energy. There is more, the particles travel faster. When they travel faster, there's more collisions, and with constant pressure, that's going to cause expansion. So again, going back to this is that equation rearranged, that force over pressure is area. So if you increase the force by increasing the temperature, it's going to make the area go up, which in this case is the volume. It's expanding. Again, this is if we're holding pressure constant and moles constant, because we could likewise change that. Now, if we plot this, we don't get like a kind of an exponential asymptote curve. We get a linear plot. Now, this is showing 4 different experiments where it's linear, and we can see in all of them as the temperature drops, the volume is decreasing. Here we're seeing an animation over a balloon that's somehow not flammable or melting. It expands, again, representing when you put ice under a balloon. If you put a balloon in a freezer, it's going to decrease its volume. And so for this one, they're directly proportional, and we again can find a constant, but it's not the product, it's the quotient. So the volume over the temperature is going to be a constant. So just like the previous one, we can take any 2 points on one of these lines and say the initial volume over temperature, that ratio will be equal to if you change it and take the volume over the temperature. So this is known as Charles's law. And probably one of the most important things to keep in mind here is that temperature has to be in Kelvin. So whatever you measure in Celsius, you have to add 273. Now, the reason we have to do this is set up as a proportion. So imagine if we're going to say we double the temperature from 1 to 2, then we would expect the volume to double from 1 to 2. And if we're looking at the Celsius and Fahrenheit scale, let's pretend we're going from 20 to 100. Well, setting up as a ratio, 20 to 100 is an increase of a factor of 5. That's a 400% increase. But technically, it's not. Considering that thermal energy starts at 0 Kelvin, then we're not going from 20 to 100. We're going from 293 up to 373. So proportionally, that's a much smaller increase in thermal energy. So we have to use the absolute value. It's this type of analysis of gases that led to the discovery of absolute zero. So you can see on these plots, this is just showing 4 different experiments at different pressures. but they all decrease, and then there gets to be this point where it's a dotted line. And you could probably guess what happens to gases when they get too cold. They condense. And so this is where they start they liquefy, and gas laws don't behave as liquids. So what this is showing is extrapolation. So take the slope of the line and continue it on. And what they found was they all tend to converge to a single point. So where they would predict the volume of the gas would have zero volume, was it all happened to fall right at 273 degrees Celsius. And this is where Lord Kelvin, he theorized this point of absolute zero, negative 270. The next law we have is the Gay-Lussac's law. So this one also deals with changing a property with temperature, but specifically pressure. And so now instead of holding pressure constant, so we're looking at a constant volume. So here we have a constant volume container, and so as you heat it up, again, you would probably know you shouldn't put like a soda can in the oven or something that has a confined space, because we know the volume wants to go up, but if the volume doesn't go up, it's the pressure that's going to rise. So as temperature goes up, pressure goes up. Again, they're directly proportional, and we can easily say, again, going back to this equation, the force is going to go up, and if it's not the area changing, it's the pressure. So increasing temperature increases force, increases pressure. So again, particles are moving faster, and with more collisions on the surface, that equates to greater pressure. Again, the ratio is a constant, so we can set up P1 over T1 equals P2 over T2. The last of the gas laws is, I think, the easiest. It's called Avogadros Law. We've heard of that name. And while Avogadro's number was named in honor of Amedeo Avogadro, this one was actually determined by him. So this one is simple. As you pump more particles, more molecules of a gas, the pressure and or volume will go up. If you decrease the amount of gas, the volume or pressure will go down. Easily seen with the balloon. As you blow more and more and more air into it, it's not because you've lowered the pressure, it's not because you've increased the temperature, it's because there's literally more particles of gas crowded into that same space. So Avogadro first determined that the volume of a gas does not matter on its identity. So on its molecule size, how many atoms, only the number of particles. So we can say the number of particles is determined by moles, N, and as the moles go up, the volume goes up. So again, this one is plotted, it's linear when you plot them together. And so the ratio is V1 over N1 equals V2 over N2. So if you double the moles of gas, it doubles the volume. Now, the alternate form of this, if you were to hold the volume constant, the pressure would go up. So if you imagine like filling up your car tires, where not from flat, but from 40 psi to 60, as you're pumping more gas particles in, and the pressure goes up because the volume is constant. Now, besides this connection, there's another way I want you to know that this plays out. And for chemical reactions, because all that matters is how many particles, it doesn't matter if it's teeny tiny hydrogen or great big nitrogen or ammonia in the middle. All that matters is when you balance it, 3 moles plus 1 mole makes 2 moles. Or in this case, you have 4 moles or 4 volumes of gas, and then they make 2 volumes, 2 moles of gas. So it doesn't matter that we know mass is conserved, but in this case, for chemical reactions, volume is not. So again, mass is conserved, but if the number of gas particles goes down, like in this case, we have 4 moles of gas in total going down to 2 moles, volume goes down. Volume is not conserved. Again, your sophomore year, we did a lab like this where we this is probably baking soda and vinegar, and we're getting this balloon filling up. So the products take up more space than the reactants because they're gaseous as opposed to solid. This is how we typically actually even get around. So if you think of this is a 4-stroke internal combustion engine. So a simplified version of what makes your go-go mobile move. On number 1, it's intaking gasoline. Number 2, that spark you see, that is the spark plug igniting it. And so after that spark, that explosion that's lighting the fuel, it generates gaseous products that want to expand. And upon expansion, it does the work. It pushes this piston down. And then number 3, it comes back and pushes out the waste, and it can just cycle again and again and again. But anytime we talk about guns, rockets, bombs, anything that there's work done because of a chemical reaction, it's because it's producing gases. So again, if you want to make here's a makeshift potato gun. You put a fuel like hairspray in, then you ignite it. The gases, the reactants react to make more products of gaseous products, and it expands to increase the pressure, and then bam, it goes blasting out. Again, if you look at most explosives like bombs, TNT, this is trinitrotoluene, a solid, but upon detonation, you end up with nitrogen gas, carbon monoxide, water vapor. So again, you're getting all these gases generated, varied from something that was condensed. So these are pretty simple to work on their own. And here, you wouldn't, many of you wouldn't even really have to do the math. Helium's in a container that's 3 liters at 4 atmospheres. If we double the size to 6 liters, what's the new pressure? So from Boyles Law, I want you to know that they are inversely related. So if the volume goes up, the pressure is going to go down by that same factor. So we could plug these numbers in, and we get 4 times 3 divided by 6, and we get 2. So if the volume goes up from 3 to 6, the pressure goes down from 4 to 2. With Gay-Lussac's law, we said it deals with pressure and temperature, where Charles's law was temperature and volume. If the air in a container is pressurized rapidly from 1 to 5 atmospheres, what's the new temperature? So with these two, Charles and Gay-Lussac's laws, you just need to know it has to be in Kelvin. So don't use 25 Celsius, use 298 Kelvin. Because then when we calculate our new temperature, we get 1490, which is about 2000 degrees Fahrenheit. And your sophomore year, I might have showed you this, the fire syringe, or here's a link you can click, but you can ignite small amounts of flammable materials just by pressurizing it very quickly. Because as you pressurize it, you have all that motion in a smaller area, and that's what temperature is. It's how much motion is in a given area. Here we have a flat tire that we're filling up with 1.5 moles of air up to 3.8 and started at this pressure. Well, what's the new pressure? So again, most of these are you just plug the numbers in, you do the math, and by whatever ratio the volume, the number of moles went up, that same ratio of the pressure went up. Now, you won't have these easy on the quiz and test, where you only have one thing changing, but I do want you to know the relationship. But in a little bit, we're going to look at where we combine these gas laws, because it'll be more common to have multiple things change instead of just one. So with looking at the gas laws, we have Boyles' law is inversely related. Charles and Gay-Lussac's law look at temperature changing volume and pressure. Avogadros looks at how volume changes with moles. And if we combine them, that symbol did not translate to Google Slides. This is supposed to be a time. So just moles times temperature over pressure. We said that this is saying it's proportional. So as this ratio goes up, so does the volume. If we want this to be an equal sign, we have to add a we have to add a scaling factor. And this is bugging me. Yeah, these are both supposed to be multiplication. So P times V over N times T. And so what we find is if we take this ratio for most gases, this ratio will equal a constant. And you could change some of these values, like heat up the gas or pump more air in, and they will change. The others will change in response so that they still equal this constant. So this brings about the ideal gas law, PV equals nRT. And we like using this gas law because it's fairly simple, and that's why it's called the ideal gas law. So if things are ideal, then things are simple. Now, for this to be ideal, there can't be any intermolecular forces, which a lot of times that's a good assumption, because in the gas phase, particles are too spread out for intermolecular forces to grab hold of each other. However, in a little bit, we'll talk about the exceptions. But for right now, there's going to be a couple of questions where you'll need to come back to this PV equals nRT. So first thing we need to know is, what is this constant? Because when you see it, it'll be sort of like if you need to find the area of a circle and you know you need the constant pi, well, you need to know, well, pi is 3.14. Well, what is r? Well, to do that, we just need to take any sample of gas and look at what these measurements are and plug them in. So the variables we're going to choose are what are called standard conditions. So 0 degrees Celsius and 1 atmosphere. So experimentally, you could take 1 mole of a gas at these conditions, and we'll find that it takes up 22.4 liters of space, regardless of the identity of that gas, whether it's neon or methane or argon, CO2, they'll all take up the same amount of space. Because, again, that's Avogadros Law, that the only thing that matters is how many particles. So now, knowing this, if we plug in 1 atmosphere, 273 Kelvin, those were standard conditions, and now we have 1 mole takes up this volume, we get a value of 0.082057. And the units look kind of scary, liter atmospheres per mole Kelvin, but they're actually pretty friendly. And what's more, they're going to tell you what units you need. So on the quiz and test, you'll be given this constant, and when you see these 4 units, it tells you you have to convert everything to those specific units. Let's go ahead and try. So we have 9,500 milliliters of sulfur hexafluoride, 5.9 grams of it at 19 degrees Celsius in a steel container. We want to know, what is the pressure? So starting with the ideal gas law, we have a volume, we have a amount, a mass, we have a temperature, R is a constant, we're looking for pressure. So really, these questions can be pretty easy. You just have to do some conversions. So first, we have the fact that there's 5.9 grams. Well, I'm hoping you remember from earlier in the semester how to go to moles, and it's simply just dividing by the molar mass. And I'm also hoping you could still come up with that number. So N is 0.0404 moles. Next, the temperature is 19 Celsius, but we have to add 273 to get Kelvin. The volume is 9,500 milliliters, but we need 9.5 liters. And then R is just the constant, it's the number. So when you plug everything in, if you're one to follow units, liters cancel, moles cancel, kelvins cancel. The only thing that gets left over is atmospheres. And so here we go. We get 0.106 atmospheres of as our pressure. Here's another one that I would have you work had you been here, but you're not. That's okay. This is sodium azide. You find it in airbags. So upon impact, a sensor will trigger it by heating it up a little bit, and it will decompose to give off nitrogen gas. So we want to know if 37.5 liters of N2 is given off at this temperature and pressure, how many grams of nitrogen would that correspond to? And so again, we're starting with PV equals nRT, but this time, if we need to know how many grams, we need to first of all figure out how many moles there are. So our pressure is in atmospheres. Again, if we had millimeters of mercury, we would need to change that. Our volume is what we're looking. Our volume is given. R is a constant, and temperature just needs to be converted to Kelvin. So taking all of this, we get 1.4 moles of nitrogen. So then you need to know, how do I go to grams? And it's by, I skipped it, multiplying by its molar mass, 30, to get 39 grams of nitrogen. Okay, now I mentioned gases are not always ideal, and when they're not, we call them real or non-ideal gases. Now, this happens for in a few scenarios. Now, again, by definition, it's if you take the ratio of your gases and they no longer equal 0.08 to 1. So this can happen a number of ways. So for one, some gases just naturally have high densities, and by definition, a dense gas or a dense substance has particles really close to each other, something like xenon. Another scenario, any gas, if you increase its pressure up above like 5 atmospheres, by increasing the pressure, it therefore increases density. And lastly, low temperatures. So as temperature goes down, again, think like as you approach the boiling point, or in this case, you could call it the condensation point. As they get closer and closer together, as temperature drops, the particles aren't moving with as much kinetic energy. And again, what those all have in common is the attractive forces start taking over. And so when there's any of these attractive or repulsive forces coming into play, when intermolecular forces are no longer negligible and insignificant, you can no longer calculate these values when that happens. Now, another use of this is we can talk about, instead of a static, so the ideal gas law is used for a static, like a sample of gas. So just think of a gas tank or a bottle or even the air. But what if we want to look at changing multiple things? So again, if we take this and solve for R, we say R is constant. So we can change these variables, and these will change with them, but R stays the same. So setting them equal together, we get the combined gas law. And so this will be used when there are multiple things that can vary. So we can show that you can technically we're going to use this for anytime any variables change, even if it's just one. So imagine this light bulb you flick on and the temperature goes up. Well, how does the pressure change? Well, the amount, since it's an isolated system, the volume and the moles of gas stay exactly the same. So if you factor those out, you get Gay-Lussac's or Charles's law. And so then it's just a matter of plugging everything in and solving. Now, you can expect a little bit harder one than this, because it's more common to have multiple things change. So here's a scenario where if you're looking at a bubble that's at the bottom of a lake that rises up as it ascends, you're going to see it gets bigger for two reasons. The pressure drops, and so as pressure drops, volume expands, and the temperature goes up, and as temperature goes up, volume expands. But how much bigger will it get? And we could say that if it's an isolated bubble, then the moles of gas is constant, and we can factor that out, and we get this, PV over T equals PV over T. Here's a video that explains what's going on here. Essentially, certain lakes, this one's in Russia, there's methane that bubbles up from underneath the lake, but it gets trapped underneath the ice. And so you get these pockets of methane gas that you can free and then ignite for what looks like a lot of fun. So we use these laws just like the single gas laws. Now, because it's a ratio, unlike the ideal gas law, it is okay to use milliliters. You don't have to change to liters. However, you still have to use Kelvin. So you still have to add 273 to find that final volume. So our gas bubble went from 2 milliliters up to 14. Now, here's one that I would have you work out in class. So if you want to double check your abilities, you can hit pause and solve. But this one is a helium balloon the size of a basketball that floats up from sea level to the top of Mount Everest. So as the pressure drops, the volume expands. But as the temperature drops, we would expect the volume to get smaller. So here we have two contrasting opposing variables. So again, you would set it up using this where if it is a fixed balloon, you could say N1 and N2 are the same, so they're not actually given. So again, pause the video if you want to try to do this on your own. And then 3, 2, 1, here's the answer. 17.8 liters. So again, you can work the ones in the homework because I don't know. I have a strong suspicion not a whole lot of you hit pause and actually worked it out. But maybe I'm wrong. Yeah, I'm probably wrong. So the last gas law of the chapter is Dalton's law of partial pressures. Now this one is kind of different from the others. This is a pretty simple observation that if you combine gases, that the volumes are conserved. Now that might not sound super groundbreaking that 1 liter plus 7 liters equals 8 liters of gas. Or here we have the pressures under constant volumes. Again, the pressures are cumulative. But what's notable about this is not true for solids and liquids. Solids and liquids, their total volumes can change, not drastically, but parts in small amounts because their densities vary. So as things pack together in the condensed phases, the volumes and pressures can not be absolutely conserved. But in the gas phase, upon mixing, since the amount of space doesn't depend on the identity, we see that the volume and pressure are completely conserved. So total pressure, the individual pressures will add up to the total pressure. So we're going to use this to talk about what if we have a mixture of a gas and we want to know what is the partial pressure. So this I is for individual pressure. So the T total pressure is the sum of the individual pressures. So what we want to be able to do is figure out what is the partial pressure. And to do that, we're going to take the mole fraction. Now, the mole fraction, just like the name suggests, it is a fraction of moles. So on the bottom, the total number of moles of gas. On the top, the moles of individual gas. And so it has this italicized X. And so once you know it, then if you know the total pressure, multiply by the mole fraction, and you have the individual pressure. So let's try using that. So 90 grams of neon, blah, 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 blah. So we have these three masses of gases mixed together, and the total pressure is 2 atmosphere. What is the partial pressure of neon? So we need to know what is the mole fraction. This should be a multiplication sign, but it converted weird. So we know the total is 2 atmospheres. We need to find the mole fraction of neon to get the partial pressure of neon. So first, we use the molar masses. Oh, that converted to like an emoji version. That's neat. But 90 grams of neon divided by its molar mass, all of these divided by their molar masses give moles. So then we want moles of neon over the total number of moles. So on bottom, we add them all up. On top, just neon. So we get 0.6. So effectively, in terms of the number of molecules, it is 61% neon. So if 61% of the gas is neon, then 61% of the total pressure is from neon. So the partial pressure of neon is 1.2 atmospheres. You can try that for xenon and argon if you like. And that is the end of this video. We'll pick up, I'll post another video next week or this week to finish out this chapter on Tuesday, and we'll start with finding the density of gases.